Hello everyone, my name is Bin Ouyang. I'm a material scientist working in the field of computational material science and autonomous synthesis. This is my research channel for sharing my understanding of material science. I will post either my understanding of papers, some mini tutorials of material science, as well as some funny things as a material scientist. Please subscribe if you want to get up-to-date information from me. Currently, I'm a postdoc working with Professor Gerben Cedar at the University of California, Berkeley. This is the second part about short-range order and lithium transport in fluorinated disorder rocksalt cathode materials. All the details of this video can be found in these two published papers. From the last video, I have introduced how to establish a computational framework so that we can generate some atomic structures so that to simulate the short-range order we see in experiment. And I have used electron diffraction patterns as an example to show you how these atomic simulations agree with experimental observations. From these comparisons, you know that we can actually now deconvolute this compressed information in experiments, right? Because in experiment, we only get a compressed information because, for instance, in the case of TEM, we can only get an image from a certain zone axis. And then we can only get a collective information of short-range orders by just looking at these diffusive patterns, right? But now we can have a 3D atomic structures from the computational framework. And with these structures, we can really look into what are the atomic local units that are responsible for what we see in characterization. So with this kind of tools established, we can now move to the last stage. We will be able to predict the performance of the materials. So here I list 4 groups of materials, which are nickel tie, manganese tie, nickel niobium, and manganese niobium. These 4 groups of materials have the redox center being 2+ cations. And this is actually good for disorder rocksalt. As I mentioned in the last video, that we can enable 2 to 4+ redox. So intrinsically, you will have double the redox capacities compared with the case of 3 to 4 redox. And here we can use the atomic structure that we get to simulate the 0Tm percolating lithium as a function of fluorination amount. So if you remember in the last video, I mentioned that in the disorder rocksalt materials, the performance is largely decided by the amount of 0Tm channels and how can those channels percolate in the bulk. So in that case, the percolating amount of 0Tm channels would be a very effective merit to estimate the amount of lithium that you can extract kinetically. So here we plot the amount of 0Tm percolation lithium as a function of fluorination amount. So first of all, you can observe that at 5% of fluorination, you will have minimum amount of percolating amount of lithium. So that basically tells you that 5% of fluorination is probably the worst composition you want to deal with. And then if you keep increasing the amount of fluorination, you will reach a very high amount of percolating lithium at over 20% of fluorination. And that indicates that if you can heavily fluorinated disorder rocksalt oxide, you're probably going to end up with very good kinetics. And another thing you want to keep in mind is like as you keep fluorinating the materials, you will end up with a lot more local lithium-rich environment, which is lithium-6 fluorine. That kind of explains why in the end you're going to have a lot of percolating lithium, because you're going to form a lot of lithium-rich environment in the bulk. So now let me take a careful look at why at 5% of fluorination, the performance is actually the worst. So since everything is about percolation, right? So you can look at the percolating amount of lithium, which is essentially the critical part for zero-TM percolation. But on the other hand, you should also look at the isolated zero-TMs, which means even though you can form some lithium-rich environment in the materials, they may not connect well with each other. So the lithium can only move fast locally. So in that case, if you plot the amount of isolated zero-TM channels as a function of fluorination, you will realize that whenever the percolation reaches the minimum, the amount of isolated zero-TM will reach its maximum. That basically illustrates that the reason why you have bad performance at 5% of fluorination is because that you form a lot of isolated zero-TM channels in the materials. And now if you look at the physics picture that I mentioned in the last video, you probably will understand what exactly happens. So if you have a 2+ in the materials, they prefer to directly bond with oxygen, right? Because they can form a local charge neutral. But if you have a fluorine, now the charge neutral will be broken because fluorine have a 1- anion charge state. And in that case, it tends to attract a lithium, and the transition metal will thus mix with lithium, so that you will create a lot of these 1TM channels, which is made of lithium-3 and 1 transition metal in a local tetrahedron. So that is actually bad for the performance. So if you check the amount of 1TM channels, which is lithium-3 metal, as a function of fluorination, you will see that we're going to tend to form an increased amount of 1TM channels with the increase of fluorination. And if you keep fluorinating the materials, it will finally drop. And then you will end up with very good kinetics because you tend to form a lot of lithium-rich environments, and those environments will connect it well with each other. So with this kind of tools, now we can move a little bit further, right? Because like 6 years ago, we can use a random model, as demonstrated in this work, to predict what happened in a random alloy. So we know that we need to go lithium excess. So statistically, we have a lot of zero-TM channels, right? But from this video, I told you that this is not the only thing we need to care about, right? Even though you can form a lot of zero-TM channels, if they cannot connect with each other very well, you will still have a bad performance. So with this computational framework, we will be able to establish a percolation map for realistic compound at realistic synthetic conditions. So here I give example of manganese 2+ niobate 5+ systems. So the first information you can get is that at which condition you can make this material at a given temperature, right? So usually we tend to use solid-state synthesis to make those materials. So we can establish an equilibrium phase diagram at high temperature, which here I use 1873 Kelvin as a synthesis condition. And in that case, you will have phase separation in the shaded region, which suggests that you may not form the disordered rocksalt phase. And at the same time, you can also keep track of the evolution of the performance as a function of the compositions. So the X and Y represent the lithium amount and the fluorine amount of a disordered rocksalt. So when you tune this amount of compositions, you are essentially manipulate the properties of the materials, right? Since the color map tells you the amount of percolating lithium per formula unit. So then you can use this map to capture 3 things, right? So first of all, you can capture the kinetics. Secondly, you know if you can synthesize these materials at a given condition. Thirdly, you can also keep track of the electron capacities of the materials because, as I mentioned, we also need to make sure that we have enough electron capacities. That is actually the reason why we want to fluorinate the materials, right? So the contour lines here basically tells you the amount of electron capacities that you can get from the materials. So with this kind of a map, we can do a computational screen of the chemistries that we want to do, right? And here I give you example about one promising chemical space that we have found. And with this kind of a map, we can actually also predict what's gonna be the best composition we would like to work with, right? So here I showed you a lithium manganese oxyfluoride, where manganese have a variety of oxidation states. So that is why you can establish this map with 2-degree freedom. And with this kind of a map, first of all, we found that you can synthesize these materials with Bohr-Milling conditions, so there's no miscibility map. And then you can use this performance map to predict and roughly estimate what's going to be the best region to work with. So there are two trends going on here. The first trend, if you look from the right top side to the right bottom side, you're going to see that the amount of extractable lithium by 0Tm percolation gonna increase from the top to the bottom. And that basically tells you that if you want to have a good percolation, you should avoid high amount of fluorination up to 33%. It may get better after 33%, but before that, the oxide will be the best. So we actually confirmed that in experiment, and these 4 compositional points, I also marked it in the experimental voltage curve here. So it basically tells you that when you go from compound 1 to compound 4, you have monotonically decrease of capacities, which is consistent with the fact that you're going to have less extractable lithium kinetically. But this is not the optimum option, right? Because the contour lines actually tells you that in the right bottom side, you have the smallest amount of electron capacities. More specifically, compound 1 is actually lithium manganese oxide with manganese staying 4+. This kind of a compound has no electron capacity at all. So in that case, you will rely on those irreversible oxygen redox. So at this kind of situation, you probably want to move from right-hand side to the left-hand side, right? Because the contour lines will show you a larger number, which indicates a higher amount of electron capacities. So in this case, even though you're trying to decrease the amount of percolating lithium, you are actually increasing the electron capacity of the materials. So in the end, you're gonna gain retention performance of the materials. So here I give example as the experimental retention comparison between compound 2 and compound 5. Even though like compound 2 start with a very high capacity, it decays very fast because the lack of electron capacities. And as a compound 5, even though it has very good, even though it has relatively less capacities, the retention turns out to be very good compared with compound 2. So in that case, by looking at this map without doing any experiment, you probably know that this will be the region that we want to work with. It's more like a trade-off of redox capacities as well as the kinetic accessible lithiums. So with this kind of a map, we can really achieve theoretically guided experimental synthesis and optimization of these disorder rock salt materials. So to summarize, I hope my video gives you a flavor of how to understand the short-range orders and of fluorinated disorder rock salt materials. And I hope you are convinced about my explanations and my understanding about the experimental capacity evolutions as well as the retention evolution of those materials. And that's pretty much about my presentations. And in the end, I'd like to give a hint on the fact that when we design the materials, such as this lithium with several metals, with oxygen and fluorine, it has really a large combinatorial space. The establishment of those design maps from theoretic tools will not only help us to understand what exactly happened and to review the atomic structure behind those convoluted characterization. It also can help us to reduce a workload in exploring those chemical space. So that's pretty much about my presentations and also about these two works. I hope you enjoyed this video.